Hi everyone, let's start with the today leetcode problem. So today leetcode problem is maximum level sum of a binary tree. So let's read the problem statement and after that we can try to come up with some working solution for this one. So we have been given the root of a binary tree and the level of its root is 1 and level of its children is 2 and so on. Okay, makes sense. So we need to return the smallest level x such that the sum of all the values of node at level x is maximal. Okay, so let's try to understand this problem statement using some example. So we will use the given example. So let me just create the binary tree. Okay, so as per the problem statement, the level of root node is 1 and level of its children node is 2 and its children node is 3 and so on. So it would continue like this. Okay. So if we see the total number of nodes that we have at level 1, we see only one. At level 2, we have two nodes and whose values are 7 and 0. And at level 3, we have two nodes whose values are 7 and minus 8. Okay, let's do the summation because we have to sum all the values of a node at any particular level and then we have to return the smallest level which has the maximum sum. So for this one, if we see the sum is 1, for this one the sum is 7, and for this one the sum is minus 1. So definitely like this 7 is the maximum one, so that's why we are returning this 2. Okay, so let's try to come up with some custom input. So let's say like we have this 1, 2, 3, and 1 and 4, something like this. At level 1, if we see the total sum of all the nodes is 1. At level 2, the total sum of all the nodes are 5, and at level 3 also the total sum of all the nodes are 5. Okay, so here we see like we have two sums or two levels where the sum is maximum or equal, that is 5 and 5. So among that we need to return the smallest level, so that's why for this input also we should return output as 2. Hope you understand the problem statement clearly. So let's try to come up with some algorithm to solve this problem. Okay, so first we'll try to come up with some brute force approach and after that we'll try to optimize our approach. Okay, so one natural approach that is coming to my mind. So definitely here like we have to traverse the entire tree level wise. Okay, so that at any point of time for any of the level we should have the sum of all the nodes and we can take a call and return the output. So we have to traverse our tree level wise. So we know for this level order traversal, the standard approach or the standard algorithm is PFS. Okay. So we will utilize the same approach for our use cases. And the another algorithm through which you can traverse any tree are DFS. And under DFS, like we have multiple ways, like in order traversal, pre-order traversal, and post-order traversal. But we should stick to level order traversal, that is PFS algorithm, to solve this problem. Okay. So now, like the standard VFS we will utilize. So let's recall the standard VFS approach. So in standard VFS, what we used to do, like we use some data structure that is queue, and we start processing all the nodes that is present at a particular level. So after performing the VFS for this one, we would have 1, 7, 0, and 7 minus it. So that we also want. We will just do the simple math here and perform the summation and after that we can solve our problem. Okay, so our approach will have two steps. One is perform the standard DFS, and what we can do, we can store this values in some data structure. Let's say like we are using map, okay, to store these values. So in our map the key would be the level and the value would be the summation of all the nodes that is present at that level. Summation of all nodes. After that, we would have a map data structure after this step. So let me represent that map. For 1, we would have 1. For 2, we would have 7. And for 3, we would have minus 1. So this is the state of the map that we would have after we perform the step 1. That is the standard PFS. Okay. And after that here, if we have our map ready, then what we have to do? We have to simply sort this map okay, on the basis of the value, and accordingly return the level. Okay, so while performing the map also we should write our own sorting logic that would ultimately help you to handle all the possible cases. So here if you see, like, we have all the summation, that is 1 7 and -1 are unique. There could be a case like at level 1 also we have some as 7. Then in that case we have to return the smallest level, so the output should be 1 instead of 2. Okay, so we should write our own custom logic to perform the sort. Okay, sort the map with custom logic, own logic we can say. Okay, so we identify our approach. Our approach has two standard steps. One is performing PFS, and after that we are sorting the map with our own logic. Our logic. Let's discuss our logic. What would be our logic? If values are different or unique, then sort by value, and if values are same, then sort by key. Okay, that would solve our problem for all the cases. So now we understand our approach. Let's try to calculate the time and space complexity for this approach. So if we see, we have two standard steps. So first step is the standard BFS. So for this one, the time complexity would be order of n. And for the sorting, the time complexity would be order of n log n. Let's say like we are using the library sort, and that library sort is kind of very optimal. And the worst case time complexity for this one could be n log n. Okay, let's define what is n here. So definitely this n is not the total number of nodes. Let's try to identify what is this n. So this n should be the size of the tree. Okay, so at any point of time, whatever would be the size of our map will be equals to the size of the tree or the height of the tree. But our tree in worst case scenario can go up to n. For example, this pine rescue tree. Okay, so here the height of this tree is 3 and total number of nodes is also 3. Okay, so in worst case our time complexity for performing the sort operation would be n log n. Okay, so let's talk about the space complexity. So here we are using a map to store all this information. So for that one, in worst case, considering this fine rescue tree, we could have order of n space. So the space complexity would be order of n and time complexity would be order of n log n. Okay. So for this approach, this is the first approach that comes to my mind. So we could have another approach also. So let's try to come up with some another approach. So at any point of time, what we need the smallest level x. Okay. So is there any data structure that allow us to perform this getting the smallest element or maximal element efficiently? Yeah, we have. Okay. So we should use some heap, and here at any point of time we need to return the smallest value, so we should use a min heap. In our min heap we should store both the information, the label and summation. Okay, so instead of using map we are using heap, so that we don't need to perform the standard sorting part there. So let's now try to calculate the time and space complexity. So here we are first, our algorithm will have performed BFS, and second would be like in our heap, or while performing the BFS only, like insert the elements into the heap, and third and the final step would be return the top element. That would solve our problem. Okay, so the heap that we need to create, we need to be conscious because we have to perform the same sorting logic. in heap also. The same logic that we have discussed for map. So while creating an instance of priority queue, we should implement our own custom logic. So that would take care of everything. Now let's discuss the time and space complexity of this approach. This is approach 2. So the time complexity would be for this standard PFS, the time complexity would be order of n, and for inserting the element or any single element into a heap, the time complexity is log n. Okay, but we need to insert n element, so the time complexity for inserting the elements would be n log n. Okay, so overall time complexity would be order of n log n. Okay, and the space complexity would be order of n because we are inserting all the summation or for each of the level in heap, and in most case considering the binary skew tree that we have just discussed. Okay, so the space complexity would be order of n. Okay, so this is the time and space complexity. Here if you just compare your first approach 1 with approach 2, you will see the time and space complexity are same, so there is no change in the time and space complexity. Okay, so let's try to see like can we do better or not. So for that one, what we can do, let's try to think and try to optimize the time complexity or space complexity further. So in our approach, like we understand our approach has two steps. One is performing the BFS, and after that the second one where we are either inserting into the map or into the priority q1 and accordingly like calculating the final result. Okay, but at any point of time do we really need to worry about other levels information, like at this level we have this summation and at this level we have this summation. At any point of time we are just interested in inserting or returning the smallest element, so we should not store or we can avoid storing all this unnecessary levels information. So in that way, definitely like we can optimize the space complexity from order of n to order of 1. Okay, because at any point of time we just need to return the smallest level x. Okay, so then why we should worry about all the level information? We can skip that one. And now let's focus on how can we calculate, because we are persisting all this information in some extra space so that we can calculate the final result, that is the smallest level one. Okay, then how can we calculate this smallest level one? Okay, so for that one, like while performing the standard BFS only, they're only like using some custom logic, we can integrate this logic part to calculate the smallest level x. So let's say like I started performing the normal BFS, so here I done the summation. Okay, I also know the levels. Okay, in the next one I done the summation and I also know the levels. Okay, if I compare the sum value for this level 2 with the previous level 1, we know like the second level summation is higher, so we should use or we should update our result set. Okay, so let's say like in our result earlier we are storing both the information level and sum. Okay, we check and we compare and we updated it accordingly. For the third level also, like we have minus 1 total summation and the level is 3. Okay, and we see like this minus 1 is definitely smaller than the 7, so we are not going to update our result. And at the end we will just return this current level, that is 2. So in that way, like what we can see here, the time complexity we have reduced from n log n to order of n. So for this approach, the time complexity would be order of n, and space complexity would be order of 1, because we just need one variable where we will store this information and at then we'll just return the result. Okay. Now let's try to code the solution and try to submit it. So I'm just doing the standard check. If root is null, then we are returning 0. But that could not be the case. If you see the constraint here, the number of nodes in the tree would be in the range from 1 to 10 to the power 4. So definitely like there would not be a case when the root is null. But just as standard practice, I included that statement. Now let's try to implement the standard BFS here. So in just implementing the standard PFS one, so I just inserted my first element to process, okay, in my queue. And after that, as soon as like we have elements to process in our queue, we'll continue our loop. And as soon as like we are done, basically we have processed all the elements, then yeah, we are done with the PFS, and we should update our logic or did write our logic in such a way like at the end of this PFS one, we have our result ready, we can return that one, okay. So let's calculate the size, because at any point of time we need to iterate or perform the summation level wise. So for first level, I will do the summation of all the nodes. For second level, I will do the summation of all the nodes. Let's just create a few variable to store the level sum, as its name suggests, for this level or at any particular level for which this processing is going on. I will store the summation. Let's try to perform the top operation or full operation to fetch the top element, and as soon as like it has elements or left node and right node, we should start processing that one also. So I'm checking for the left node and accordingly inserting it if it is not null. Basically it is present here. Same applies to the right node. Right node is present, then definitely like we should not skip that one. We should insert that one in our queue and start processing for that one. Okay, makes sense up to this point. Now for this level, like we should start performing the summation and start updating our level sum variable. Okay, so now like for any current level, let's use one variable label, and the default one is one, because as the problem statement states, the level of its boot is one. Okay, and as soon as like we are done with the processing of all the nodes at any particular level, we need to increment our level. Okay, makes sense up to this point. Now, as we discussed in the optimal approach, we should just have one variable where we should store this level information and the summation information, and we should update it whenever we are finding any level that is having the maximum sum, and at the end we should return that result. So let's say like I am using, you can use pair also if you want, because you need to store two elements, but here for simplicity I am using an integer array of two size. Okay, for level 1, that is the parent level 1, we know its level is 1, so result 0. Let's say like at 0th index I am storing the level, okay, and at index 1 I am storing the summation. So for the first level we know only root element is present, so we have already performed the null check, so we are free or we are safe to fetch the value directly. Okay, now we have started our processing. We are done with the processing at this level for the first level node. Here we should take a call whether we should update our result or not. If level sum is greater than the current level sum that we are storing at first index, then in that case what we can do, we should update our results with. So we should update at 0th index I am storing the level, okay, and at one index I am storing the summation. Yeah, that's all. At the end, we can return the label. So we are storing at index 0. Okay, that's it. Let's try to run the code and see if there is any compilation issue. And if there is no compilation issue, we can submit our code and check its correctness. Okay, it seems to be working for this input. So don't be in hurry. Let's try to test it for another test cases. And let's write one of our custom test case. So it's a complete binary tree. So for input 1, 2, 3, 4, 5, the output should be 3. Let's validate it. The output is coming as 3 and the expected output is also 3. So yeah, let's try to submit this code and see whether it is getting accepted or not. Yeah, it's getting accepted with 96.46 faster rate. So yeah, that's all I have from my end today.